Hi everyone. So in this video, we're going to talk about finding the average rate of change of a function. So we're going to start off by just talking about the concept of average rate of change without really using function notation or saying the word function. But once we've kind of built up a little bit more intuition about what average rate of change means, then we'll move to talking about how it works for a function. Okay, so let's say that you have some kind of a quantity that is changing. So when I say a quantity, it's something that you're measuring. So examples could be the temperature. I know I keep using temperature as an example, but it's just a nice simple example. So like temperature, right? Temperature changes as time goes on. Or it could be population, like the population of a city is going to change as time goes on. Or distance, like say you're going on a walk or going on a drive and you're keeping track of how far you've traveled. All of those things are things that change as time goes on. And so the average rate of change is basically a way of measuring the rate at which that quantity is changing. So let me just kind of write that down and then we'll get into a couple of examples. So if a quantity, so for example, like we said, temperature, population, distance, etc. Anything that you can be kind of keeping track of and measuring as time goes on. So changes as time goes on. Then the average rate of change of the quantity over a particular time period, like so we'll see that whenever you're talking about average rate of change, you're always talking about a certain, in this case, time period or a certain range of x values. We'll see when we get to talking about function notation. But over a particular time period is going to be the change in the quantity divided by the change in the amount of time. Like basically, how much has the quantity changed divided by how much time has passed. So let's look at a couple of examples of this. So one example could be, I'll use temperature as I said, I like to use this example, but so let's say that it is 61 degrees Fahrenheit at 12 p.m. And then the temperature rises over the next few hours and it hits 70 degrees Fahrenheit at let's say 3 p.m. And actually that, I think I pulled that from my iPhone this morning. So I think that actually is what the temperature is supposed to be on the day I'm recording this video. So what we want to find is the average rate of change of the temperature over this time period. So from 12 p.m. to 3 p.m. Okay, so what do we want to do? Well, we need to figure out how much did the temperature change, and that's going to be in the numerator. And then we're going to divide that by how much time passed. So how much did the temperature change? Well, we can do that by subtracting, right? We can say 70 degrees minus 61 degrees, or you can just do it in your head. Fahrenheit. So I'm going to include units because I think that will help kind of understand what the meaning is of this average rate of change. And then how could we find the amount of time that's passed? Well, it's a little bit funny here in terms of subtracting things just because of how our time system works. So let's just say, we know that from 12 p.m. to 3 p.m., we know that that's 3 hours. We'll see that in later examples, we'll be able to actually subtract, but again, it's just because of our at least in the US, the way that we label our hours makes it a little difficult to write this as a subtraction. Okay, so what does that give us? Well, that gives us in the numerator 9 degrees Fahrenheit over 3 hours. And so we can simplify this, right? We can reduce it. And so we end up getting 3 degrees, right? 9 divided by 3 is 3. And then what are our units here? Well, I'm actually going to kind of separate out this degree symbol and write it in words. So what are the units? They're degrees Fahrenheit per hour. Oops, I don't know why I wrote hour like that. So one thing that I just want to mention, because I think this is something that's important to know just for like life, is that whenever you have a division symbol like this in the context of like units, you can think of that division symbol as being the word per, right? Degrees per hour. So how would we interpret that? Like, what does that tell us? Well, that tells us that on average, the temperature went up by 3 degrees each hour. Now, that does not mean that the temperature actually went up by exactly 3 degrees every hour, right? And that's the importance of this word average, right? We're finding the average rate of change. So we don't have enough information to know exactly how much the temperature went up at every single hour, but we do know the general trend. We do know that on average, the temperature rose by about 3 degrees per hour. Okay, let me just scooch this graph out of the way. I put it a little too high up. We'll be coming back to this in a moment. Okay, so let's do another example similar to the last one. So let's say that now we have a distance example. So let's say that so you're driving somewhere, you're going on some kind of a road trip, maybe you're driving to visit some family, something like that. So let's say that at 1 p.m., so you start driving at noon. And let's say at 1 p.m., you have driven a distance of 35 miles. So you're 35 miles from your starting point. And then 4 hours later, so at 5 p.m., you have driven 235 miles. And so what we want to find is the average rate of change of basically your distance from home from 1 p.m. to 5 p.m. And we'll see that there's kind of a better way to say it. You know, it sounds very clunky to say the average rate of change of your distance from home. We'll see that there's a much nicer word that we can use for that, but I want to first kind of phrase it this way, and then we'll interpret what that actually tells us. Okay, so just like above, right, we would want to figure out what's the change in the distance. That's our quantity, and we'd want to divide it by the change in time. So in this case, the change in distance we could do by doing 235 miles minus 35 miles, right? That would tell us how much our distance has changed. And then we can divide that by the amount of time. And in this case, we actually can subtract, right? We can say like 5 minus 1 hours. Or you could just kind of do it in your head. And so what would we get? We would get 200 miles in the numerator, and we would get 4 hours in the denominator. And so once again, we can simplify this, right? This simplifies to 50. And then what are our units? Well, they're miles per hour. And so that kind of helps us understand, you know, what are we actually calculating here? What's the average rate of change of your distance? Another word for that would be your average speed, right? If you think about it, speed is really measuring, like miles per hour is measuring how much distance is covered in a certain amount of time. Okay, so hopefully in these two examples, you kind of built up a little bit of intuition of like, what do we really mean when we say average rate of change? We're basically measuring some kind of a rate, right? Some kind of a speed or how quickly something is rising or falling, something like that. So I now want to kind of rewrite this last example we just did, but using kind of function notation, because this will help us transition to the to writing this stuff in terms of functions. So basically, let's redo the previous example. So the example about distance traveled, but now we're going to be writing stuff in terms of function notation. So what do I mean by that? Well, I mean basically, instead of just saying in words, oh, we traveled this far at this time, this far at that time, let's say that we actually have a function that measures the distance traveled after a certain amount of hours. So let's say that this function, let's call it f of x. And so what's going on with this function? Well, the x-axis represents the number of hours that have passed after 12 p.m. So remember, we started driving at noon. So like 1 hour would be 1 p.m., 2 hours is 2 p.m., etc. And then the y-axis is the number of miles that have been traveled. So f of x is a function that tells us, so let me maybe even write this out in words. So f of x is a function that gives the distance traveled after x hours of driving. So how would we go about finding the average rate of change and in this case, well, what would we say if we wanted to kind of write, not just from 1 p.m. to 5 p.m., how would we write it in terms of like variables and function notation? Well, we would say from x is equal to 1 to x is equal to 5, right? Because that is the x value that reflect a time of 1 p.m. and a time of 5 p.m. So what would we really be, putting in our numerator and our denominator? Well, the denominator is going to be the change in time, right? So the denominator is going to be 5 minus 1 hours. And, we already saw that above, but how can we interpret what this 5 minus 1 means? Well, it's coming from the fact that here we have from x is equal to 1 to x is equal to 5, right? That's where that 5 minus 1 is coming from. And then what about the numerator? How can we kind of write that in terms of function notation? Well, let's look at some points on this graph. So let's say that we have at t is equal to 1, this is the point 1, 35, right? Because we know that after 1 hour, we've traveled 35 miles. And so what that means is that this point here would be the point 5, 235. Let me get a little more space here. Because we know that after 5 hours, we've traveled 235 miles. And so what I'm trying to get at here is that the numbers that we're actually subtracting to find the distance traveled, those are the outputs, right? Those are the y values. And so how could we express that using function notation? Well, we could just say f of 5 minus f of 1, right? Because f of 5 would give us the distance traveled after 5 hours, and f of 1 tells us the distance traveled after 1 hour. So basically what I'm trying to show you here is that if you're thinking in terms of function notation, if you're finding the average rate of change, what you're really doing is in the numerator, you're subtracting outputs, and in the denominator, you're subtracting inputs. And let me just add the units of the numerator here. Because why is it that it's outputs over inputs? Well, because when you have a real world kind of situation where you're measuring a quantity, the outputs are going to be that quantity, and the inputs, the x values, are going to be time. And so this idea of doing outputs divided by inputs really matches up with the idea that we wrote here, change in quantity over change in time. And so what we'll see is that even when we're not talking about like a word problem, even when we're just dealing with like a generic function, we're still going to use this kind of setup. We're still going to be doing outputs divided by inputs. So let's go and now define exactly what it means to find the average rate of change of a function. So I'm just going to sketch a random function f of x here. So let's say this is some function f of x. Okay, so let's say that you wanted to find the average rate of change of your function f of x from, let's say, some x value that we'll call a, to another x value that we'll call b. So we're using a and b here just to represent two different x values. So the average rate of change of f of x from x is equal to a to x is equal to b is basically what we just saw in the last example. So what are you going to do in the numerator? You're going to be taking outputs and subtracting them, because by evaluating the outputs and subtracting them, that's telling you the change in the y values. So f of b minus f of a. And by the way, it doesn't matter which order you do it in. You could do f of a minus f of b, but you just have to be consistent. So if you're going to say f of b minus f of a, like we did here, then in the denominator, you would want to say b minus a. Whereas if you said f of a minus f of b, you would switch a minus b. So just make sure you're subtracting in the same order, regardless of which order you pick. So how can we interpret what that tells us in terms of this graph? So let's go in and put some points in here. So this would be the point a f of a. Oops. Right? Because if a is the x coordinate, then f of a is the y coordinate. I know it's maybe a little confusing to have all these letters here, but just think of a as representing some number. So to go back to the last example, we had 1, and then f of 1 was the y coordinate. And then we had 5, and f of 5 was the y coordinate. And so here we're just saying, a, f of a, and then this would be b, and the y coordinate would be f of b. Okay, so how could we interpret what this expression is telling us in terms of this picture? Well, it might remind you of something, right? What's something else that you may have learned in a math class where you take a change in outputs and you divide it by a change in inputs? Or another way of saying that is take a change in y values and divide it by a change in x values. So change in y over change in x, what does that remind you of? So it should remind you of the slope formula. And it actually is. It is the slope formula. So what slope are we actually measuring here? We're measuring the slope of if you were to draw a straight line going right between the 2 points on your graph. This is what's called a secant line. So this is the secant line from x is equal to a to x is equal to b. And so really one way, and I think this is a really useful way to think about average rate of change, is to think of it as being the slope of that secant line. So it's not correct to say it's the slope of your actual graph, right? Because the original function isn't even a line, right? It goes up, it goes down, it does all sorts of different things. But basically what we're doing is we're kind of imagining, what if our function was a line? If our function was a line, what would that line look like and what would be its slope? So another way of saying this is that this is the slope of the secant line. And specifically, it's a secant line from x is equal to a to x is equal to b. So I think, we'll jump into some examples in just a moment. You don't need to draw a picture and think of it as a slope of a line, but I think it's a really helpful way to kind of just check that your answer makes sense. So what we'll be doing in our next few examples is we'll be calculating some average rates of change, and then we'll go and look at the graph and visualize it as a slope of a secant line, just to make sure that it aligns with what we found as our answer. Okay, so this is, again, let me put a box around this. This is important. This is the average rate of change formula. This is what we'll be using. So again, you can either just think of it as, finding a change in outputs over a change in inputs, or you can visualize it as being the slope of this secant line. And I guess one more thing let me say before we get into our example is that notice that the secant line we drew, it doesn't really capture all of the shape of this graph, right? The graph, if we look at what happens to the graph between A and B, it goes down and then it goes back up. Whereas this line just goes up. And so what we'll see is that average rate of change is not going to exactly tell you every detail of what your function's doing. It just kind of tells you the general trend. So kind of like in our very first example, we said that we found the average rate of change of the temperature, that doesn't mean that the temperature was actually changing at exactly 3 degrees per hour all the time. It just means that that was the general trend. And then similarly here, if we look at this picture of a graph where it told us the distance traveled as time went on, you can tell that this person is not driving the same speed all the time, right? Like the steeper the graph, the faster the person's driving, right? So sometimes they're going slower, sometimes they're going faster. But what we know is that on average, their average rate of change, right, came out to be 50 miles per hour. That does not mean that they were actually driving at 50 miles per hour the whole time. That's just the average trend. Okay, so let's jump into some examples here. So these next few examples we're going to do, we're not going to be looking at the graph to start with. We're just going to be plugging stuff into functions. So first example I want to do is I want to find the average rate of change. And I'll probably abbreviate average rate of change, by the way, as average rate of change, because it's a lot to write out every time. So we're going to find the average rate of change of the function f of x is equal to 2x squared minus 5x plus 7. And we're going to be doing it from x is equal to -2 to x is equal to 1. So we know that we're going to need to evaluate f of -2 and f of 1, right? So we're going to have to go and plug those into our function. But let's start by just kind of setting up what this is going to look like. So as I said, it doesn't matter which order you subtract in. Generally, it's nice to do the bigger number first, and I'll show you why that is. So let's write down, so which of these are bigger number? 1, right? 1 is bigger than -2. So I'm going to write this as f of 1 minus f of -2 divided by 1 minus -2. So why is this the nicer order to do it? Well, if you do the bigger number minus the smaller number, that's going to guarantee that the denominator will come out positive. So if we were to switch the order and do -2 minus 1, we would get a negative denominator. And that's fine. It will balance out with the numerator, but I think in general, the fewer negative numbers you have to deal with, the better, right? So I think it's a little easier just to do bigger number minus smaller number. But again, all that matters is that you're being consistent with the order. Okay, so how do we find f of 1 and f of -2? Well, we need to actually plug them into the function, right? So let's start by doing f of 1. So f of 1 is going to be, so we're just going to plug in x is equal to 1 into this function. So we have 2 times 1 squared minus 5 times 1 plus 7. So that's going to be equal to 2 times 1, so that's 2, minus 5 plus 7. So 2 minus 5 is -3. -3 plus 7 is equal to 4. And then let's do f of -2. So f of -2 is going to be equal to 2 times, so remember here you need to put the -2 in parentheses. And then we have minus 5 times -2 plus 7. Okay, so what is -2 squared? It's 4. So we have 2 times 4. And then here we have -5 times -2. That's going to become positive 10. And then we have plus 7. So altogether, this is going to give us 8 plus 10 plus 7, and that is going to be equal to 25. Okay, so now we can go back to our same formula here and put those numbers in. So we're going to have 4 minus 25 divided by, so 1 minus -2, that's the same as 1 plus 2, so that's going to be equal to 3. So what does this simplify to? Well, 4 minus 25 is going to be equal to -21 over 3. And so that is equal to -7. So what that tells us is that on average, from x is equal to -2 to x is equal to 1, our function is going down with a slope of -7. So let's take a look at what that actually looks like on the graph. Just going to go to Desmos here. So here's our first function. So here's what it looks like. It's a parabola. And so here's the point. We have to zoom out a little bit. Here's the first point, -2, 25. And then the second point came out to be 1, 4. So that's down there. Let me actually maybe make this a little bolder. And then don't worry about where I came up with this equation exactly, but I'm just going to put in the actual secant line. And so we can see that in general, the trend of the graph is that it's going down with a slope of -7. However, we can see that the graph actually kind of changes. Parts of it are steeper, parts of it are less steep, but the average trend is that slope of -7. Okay, so we're going to do a couple more examples. I would encourage you to try some of these yourself. So they're going to be fairly similar to the last one. Although I picked these next two to each bring up something a little bit different. So this next one, we're going to find the average rate of change of the function g of x is equal to x cubed minus 3x squared plus 1. And we're going to do it from x is equal to 0 to x is equal to 3. So again, the first thing we want to do is set up our formula here. And so we're going to have g of 3 minus g of 0 over 3 minus 0. And so now we need to actually evaluate these. So g of 3 is going to be equal to 3 cubed minus 3 times 3 squared plus 1. And so 3 cubed is equal to 27. 3 cubed is 3 times 3 times 3. And then here we also have 3 times 3 times 3, right? Because we have 3 times 3 squared. And so that's also going to give us 27. And then we have plus 1. And so we end up with 1. And then g of 0 is going to be 0 cubed minus 3, 0 cubed, not 0 the 0, minus 3 times 0 squared plus 1. And that is going to be 0 minus 0 plus 1. So that's also equal to 1. And so we'll see that something a little bit different happens in this example. So we're going to get 1 minus 1 divided by, so 3 minus 0 is 3. And so that comes out to be 0 over 3. And so what is 0 over 3? Well, that's just 0. Remember, 0 divided by any number is 0. Dividing by 0 gives you something that's undefined, but 0 divided by a number, that's okay. It's just equal to 0. So what does that tell us? Let's think about this for a second before I pull up the graph. So remember that the average rate of change is the slope of a secant line. So we're going to get a little bit more into talking about linear functions in actually our next video. But you might know from a previous class, what does a line look like if it has a slope of 0? So a line that has a slope of 0 is horizontal. So let's see what that looks like in the graph. So here is the function. And here are the 2 points. We had the point 0, 1, we had the point 3, 1, and here is the secant line. So basically what's going on here is that because of the 2 points that we tried, because they have the same height, the slope of the secant line between them is 0. But I picked this example out because I wanted to show you that really, that doesn't tell us very much about what's actually going on with this graph, right? Imagine that this was a graph of temperature as time went on. That would tell you the average rate of change of the temperature was 0. And that might make you think, oh, the temperature stayed the same. But it really didn't, right? It went down and then it came back up. It's just that because the going down and coming back up kind of balanced each other out, the average rate of change came out to be 0. So again, there's really limitations on what the average rate of change can tell you. But you'll see actually when you get into calculus how the average rate of change really can be used to be made more accurate. But yeah, for now, I just want to kind of point out that depending on what your function looks like, depending on which values you're choosing, it's going to be more or less accurate. Okay, so let's do one more example along these same lines, and then we'll look at one example that's a little bit different. So this next example, we're going to find the average rate of change of the function h of x is equal to x squared over x minus 1. And we're going to do that from x is equal to 3 to x is equal to 6. Okay, so what is this going to look like? Well, we're going to be doing h of 6 minus h of 3 divided by 6 minus 3. So the reason I picked this example out is because it's going to give us some more practice with fractions, which I know, everyone I think can always use a little more practice with fractions. So let's start with h of 6. So h of 6 is going to give us, we're going to plug in 6 for x, we're going to have 6 squared over 6 minus 1. So that's going to give us 36 divided by 5. And that can't be simplified. So when we'll see an example later on in this same example where a fraction can be reduced, but basically there are no common factors with 36 and 5. So that's as far as we can simplify that fraction. Okay, h of 3. h of 3 is going to be equal to 3 squared over 3 minus 1. And so that is equal to 9 over 2. Again, that cannot be further simplified. All right, so what is this going to look like? We're going to have now 36 over 5 minus 9 over 2. And then we're still dividing that whole thing by 6 minus 3, which is equal to 3. Okay, so how do we actually combine these fractions in the numerator? Well, we need to make a common denominator. And so in this case, common denominator, we need to basically figure out what can we multiply each of these fractions by so that their denominator is the same. 2 and 5 don't really have anything in common. And so the only way to make our common denominator is going to be to multiply this one by 2 over 2 and this one by 5 over 5, because that will give us a denominator of 10 on both of them. Okay, so this is now going to become 72 over 10 minus 45 over 10, and that's still all getting divided by 3. Okay, so what can we do with these two fractions? Well, now we can actually subtract them. So 72 minus 25 or minus 45 is going to actually give us 27. So we have 27 over 10, and that's all getting divided by 3. So how do we now take this a step further to actually simplify it? Well, remember that dividing is the same as multiplying by the reciprocal. So we can rewrite this as 27 over 10 times 1/3. And so that is going to give us 27 over 30. And now this fraction actually can be simplified. So we want to look for, are there any common factors in the numerator and in the denominator? And both 27 and 30 are divisible by 3, right? Which means that we could rewrite this as 3 times 9 over 3 times 10. And so because they both have this common factor of 3, we can divide by 3 and we're left with 9 over 10. And so that is our average rate of change. Okay, so let's look at our graph of this just to get a visual on it. So here is the function. So notice, by the way, that it has what we talked about this a little bit, it has something called a vertical asymptote at x is equal to 1. The reason for that is because that's the number that's not in the domain, right? The domain, this function's not defined at x is equal to 1, and so that's why there's that kind of gap in the graph at x is equal to 1. Okay, so our points were 3 and 9/2, and then 6 and 36 over 5. And so here is our secant line, and we can see that that gives us our average rate of change is the slope of that dotted line. And in this example, notice that the actual graph is pretty close to the dotted line. So in this example, much more so than the last example, the average rate of change does give us a good idea of what's actually going on in this function. All right, we're just going to do one more example. So this one, we're going to do an example where we don't actually have a formula for the function, where we just have to use the graph. So this graph might look familiar to you. I used this graph in a previous video when we were talking about temperature. And so we're going to say that this graph is the temperature after t hours. So let's call this graph f of t. So let's say that f of t is the, or gives the temperature in degrees Celsius, just to make these numbers seem a little bit more reasonable. And let's say, I think in the last example I said T hours after 10 a.m. This time let's say T hours after noon, just to make the calculations a little easier. So what do we want to find in this example? Let's find the average rate of change of the temperature and let's do that from 3 p.m. or actually, sorry, let's do it from 2 p.m. to 6 p.m. Okay, so how do we find the average rate of change in general? Well, we've seen that basically we want to do the change in our outputs over the change in our inputs. And so if we have 2 p.m. to 6 p.m., well, 2 p.m. is going to be T is equal to 2, and 6 p.m. is going to be T is equal to 6, right? Because I chose to make it T hours after noon to just make things a little bit simpler. So that means that what we're trying to calculate here is f of 6 minus f of 2 divided by 6 minus 2. That's the average rate of change formula. Now, in this case, there's no formula or function to equation to plug these numbers into, and so we're forced to use the graph to find the outputs. So how do we find f of 6 and f of 2? Well, we just look at the y values of the points on the graph. So when x is equal to, or when t is equal to 6, we can see that the output value is 9. So we have the point 6, 9. And then we can see that when t is equal to 2, the output is 4. So we have the point 2, 4. And so that tells us that f of 6 is equal to 9 and f of 4 is equal to 2. And then in the denominator, we have 6 minus 2. And so what do we get? 9 minus 4 is 5. 6 minus 2 is 4. And so our answer is 5/4, which can also be written as 1 1/4 or 1.25. And what are our units? Well, we're talking about degrees Celsius per hour, right? Because that was the time unit. And so again, just to kind of tie that to reality of what's actually happening in this graph, that is telling us the slope of this line. But notice that it's not actually capturing everything that's going on, right? That if we look at what's actually happening to these temperatures, well, in this part of the graph, the temperature is actually going down and then it's going up. But the average rate of change is only telling us that it's going up at about 1.25 degrees per hour. And so again, the average rate of change is good at telling you the general trend, but it's not so good at telling you the specific details of what's happening at a given time. All right, so that is it for this video. Like I said, the next topic we're going to be getting into is linear functions. So we'll be doing a few videos on that, and I think some of it will be review, some of it might be new to you, and yeah, I will see you all in our next video.